straight microfins on evaporation of here 49 horizontal round tubes. The logical question, and I would like here to mention my co-author, my PhD student, Chen Yang, who had really measured all of that. And I'd like to tell you what I will talk about. Background information about previous work, objectives and approach, results, heat transfer coefficient and pressure drop, and you will see heat transfer coefficient for smooth tubes and for microfin tubes, pressure drop in horizontal and in vertical section, and I'll show you visualizations. What is very interesting in these visualizations is that I think I will show you visualization of a refrigerant flow immediately after test section, and then the start of our visualization of the evaporation in diabatic conditions with water as heating medium, so we can see what is happening in the smooth and in the microfin tube, and I believe next time I will have even a nicer from microfin straight and microfin helical flow and visualization. You will see it is very interesting and very promising. To my knowledge, microfin tubes have been visualized only at the outlet in some special conditions. The flow, refrigerant flow, two-phase flow during evaporation in microfin tubes. Microfin tubes are typically, all of those we know about are those that are helical microfin tubes, because helical orientation is always better in evaporation to kind of spread liquid all around the interior of a tube, and in condensation kind of to push stuff inside if possible by any means. Today I will talk about straight fin or microfin tube. Why straight? We know that it is worse than to do helical. Nevertheless, this is aluminum tube, and aluminum is now more and more attractive as a material in refrigeration for tubes because it is significantly cheaper. The way how microfins are made in copper tubes typically, or stainless, are two manufacturing methods. One is to have a flying mandrel. So when you work on the tube, there is a mandrel that is rotating at the same location, but the tube is twisting, and then you get a seamless but internally thin, helically thin tube. The other one is people take a sheet of copper and then make all sorts of fins or hatches or whatever. Then it is bent and welded and then smoothed. Now, aluminum is much more different material than copper, so it is easier to be extruded. When you extrude something, you don't want to have a helical tube, because when you extrude something like spaghetti, you know that very often when spaghetti are made, you have some sort of structure inside. The same way microfins are made. So, straight microfins in aluminum offer much lower cost, but we know that it won't be as good performing enhancement as helical. Maybe cost will justify the lack in performance. Basically, on academic side, we are always obsessed with increasing heat transfer. But reality is that we want heat transfer for money, for a dollar or euro or whatever currency you have. That is reality. It is not only heat transfer per surface area. Okay, so this is what I will be talking about. In this slide, you see 3 cuts of 3 tubes. The first one is a smooth aluminum. It looks here like a copper, color, but this is really aluminum tube, what you see here. The first one is smooth aluminum tube. The next one is microfin, straight microfins. You see that you can see in between the fins, basically that's straight. And of course, it is a little bit thicker tube. But outside diameter is the same, 7 millimeters. But we didn't take this tube to take heat transfer measurement, but we have expanded this tube with a mandrel as it would be expanded in a normal heat exchanger. In other words, when you push a mandrel, you deform the tips here of the microfins, and you get something like this. In that process, the tube had expanded. This is a part of this tube shown. So it used to be here, but tube expanded, and fins had been deformed, plastically deformed. Of course, if you want now to ask, okay, so what is the effect of fins? Certainly, fins will hold it a little bit. This is as much as theoretically, we could have finned the tube, run the mandrel, and then cut and remove fins, and that it would be even more realistic. But we have gone one step towards a realistic application. So I will show you results for the baseline case, and the heat transfer coefficient and pressure drop in smooth tubes have shown us pretty good results in comparison with correlations. But heat transfer coefficient in axial microfin tubes is higher than smooth. Basically, you will determine is it worthwhile, and you will see it will be something like 30% and something like 25% increase in pressure drop, and you will compare it with the price of that tube, decide whether you want to make a heat exchanger with a smooth aluminum microfin tube. Okay, this is facility. In blue is now here 410A. Look, we change refrigerant. I'll show you results with 410A. This is a test section here, and the first visualization section is over here. So that visualization section, first I will show you in kind of diabetic conditions, in adiabatic, immediately after heat transfer. And then at the end of the presentation, I'll show you some videos from diabetic condition. That means with heat transfer, actual flow regimes. Now, to adjust inlet quality, here is a calorimeter and measure that inlet quality. Calorimeter provides the opportunity with a heater, and then we measure that heater, and we can then tell you what's the quality based on saturated or subcooled liquid at inlet. We measure the flow rate with micromotion, and then we measure pressure drop in horizontal and in vertical. Both test sections are 1 meter, and then this here is just to control and circulate. We evaporate with water. Why do we evaporate with water? We want to have uniformity, even better than maybe needed. That's number one. And number two, this facility was really originally made for condensation. So same facility can be used for evaporation and condensation. And this is facility where we have measured especially condensation of CO2 at minus 30 degrees C, minus 15, minus 10. This is very important for cascades. So that is why this facility is designed in that way. The same reason is why the test section is designed as you see here. In this test section, you see very small here tube. You even don't see it. That tube is the aluminum tube. Around the aluminum tube, there are two segments of another aluminum pieces, two segments that carry thermocouples to measure wall temperature exactly at aluminum tube, which is very, very thin, to be able to groove it and insert the thermocouple. Now, these here pipes that are around and here, these are for, in this case, water and condensation or evaporation at low temperature. We put here either HFE 7100 or alcohol or something like that. That is secondary fluid for low temperatures. Now, so fluid goes here, that here in this case heats. Then there are two segments of brass material, and then aluminum and aluminum tube. Very complicated, long time to come to the steady state, but very good measurements. This is how that looks like in reality. Aluminum tube with these two aluminum segments. As you can see, we have cut it diagonally so that two cuts don't come at the same position. This is like when you put bricks and make a wall, then you don't want seam to be next to one seam, so you remove seams. And then this is how it looks like. So this is aluminum tube, test tube, and aluminum jacket, brass jacket. Here is water loop, and then insulation. Insulation is here to reduce the heat that is lost to the environment. And of course, we have done calibration and then determined this Q to the ambient measured UA value of this particular setup. Now, before we say yes, it is good, because these measurements are, as you know, very difficult because there are no two independent or three independent methods. There is only one, and that is very bad. Always, whenever you do experiment, you want to have at least one or two control methods to the main method. Here, we cannot have that. That is the reason why we were very cautiously moving forward. First, we have done single-phase smooth test. That means we have run 410A liquid. And it was very subcooled to be a little bit less subcooled, very subcooled inlet, and then a little bit less subcooled inlet at the outlet. And we have confirmed Dietz-Boelter equation. For those of you who had forgotten Dietz-Boelter, Nusselt is 0.023 times Reynolds to 0.8, Rental to 1/3. Then we have done two-phase smooth tests and compared to correlations. And it looked like something like this. Now here, obviously, these black dots with the vertical error bars are our measured values of heat transfer coefficient here and heat transfer coefficient at two different heat fluxes. And this here is 2,000 and 3,000 watts per meter square in degrees C as a function of quality from 0 to 1. Obviously, these correlations are not ideal. See how physical they are. They are not very physical, but they are reasonably okay. So we have done that. And quite frankly, not only that these correlations are not very physical, but these correlations were developed much before 410A came to the day of light. You see, shock correlation is from 76, and then you have Gunger and Winterton from 1988, and so on. So these correlations are older than fluid itself. That means even being relatively empirical, they do a decent job. There are better correlations now, by the way, but we wanted to confirm with the kind of convention. Some of them have some problems in prediction of nuclear boiling. Obviously, this prediction here over predicts value of nuclear boiling. As you know, on the left side, where quality is lower, this is a nuclear boiling dominated heat transfer, while when we generate vapor, this here becomes a more convective dominated. what do you see here in our data and all of these predictions? There is not much increase in heat transfer as flow goes from 0 to 1. What that means? In 134A, this curve would look something like this. It will go up and it will go down. Do you know when that happens? When you have and why that happens? It happens because when you evaporate refrigerant, liquid turns into vapor. That vapor, when it is very voluminous, then it creates very high velocity passing through the tube, and then increase in that velocity increases convective heat transfer, and you get something very high here. When you go to higher pressure fluid, and CO2 is even more in that direction, on the left side, nucleate boiling is much better and stronger, and that's why higher pressure fluids show better performance, because being closer to the critical point, it is easier for bubble to be generated. And when bubble generate easy, heat transfer coefficient is extremely good. So this is why this zone here, nucleate boiling, is very pronounced, while convective part is not that much, because the density of difference or ratio of difference between vapor and liquid at critical point is 1. There is no difference between vapor and liquid. So at critical point, there is no acceleration at all. So we are coming with R410A, we are going higher and higher towards critical point, and we have less and less convective component of boiling. So, by the way, the point of this slide is, it's okay. We have passed the test. Now, it wasn't so easy as it looks like in this explanation, but we had to repeat, and you see also that our error bars are maybe sizable, few percent up and down. I'd like it to be better, but that's okay. So here you see axially microfeed tube. That in the last slide, what I showed you here, that was for smooth tube, because we have that correlation. We didn't have data for axially grooved microfin tube, and this is new. So here you see that axial tube, and here you have 3 fluxes from 10 over 15 to 20 kilowatts per meter square. Over here we have, for a given heat flux, various mass fluxes. So both heat fluxes and mass fluxes affect heat transfer and evaporation. We know that well. You know, in condensation, you wouldn't have a very strong effect of heat flux, but you will have strong effect of mass flux. But this is evaporation. So these are the data. Look at this. Even now, you see that this is between 4 and 5,000, but over here, we used to have something between 2 and 3. So heat transfer is up. We already see that. Now, how about pressure drop? On the left side is a pressure drop in a horizontal tube. On the right side is a pressure drop in vertical tube. Many people, when I have asked them how much they understand the difference, pressure drop in a horizontal versus vertical, most of the people, and even many good engineers, didn't know how pressure drop in a vertical tube looks like. You know, that's very, very interesting. We are all much more familiar with the left side. What do we see on the left side? There is a pressure drop per meter length as a function of the vapor quality from liquid to vapor. We see as the vapor is generated, velocity goes up, and of course pressure drop goes up. This is very kind of obvious here. Nevertheless, in all of these cases, pressure drops start to go down. Do you know why pressure drops start to go down? Huh? There are no liquid. There is no liquid film. because there is interaction. As we are moving here up, we increase the velocity, but we have liquid at the wall. When we have liquid at the wall, there are waves on that inner wall. These waves use energy, and then pressure drop goes up. When wall starts to be dry, it is much easier for vapor to move along the tube. And that is why pressure drop goes down. And where eventually will pressure drop go? To the pressure drop of a vapor at that velocity, and that is here Dicey-Weizbach equation. For those of you who are not familiar with, you haven't shaken hands with Darcy or Weizbach, this is F L over D rho u squared over 2. So that is, this is the kind of asymptote. What are the asymptotes in a pressure drop in a vertical tube? What are the asymptotes? When you have liquid only, what is the beginning of a pressure drop? This is liquid. Liquid and hydrostatic pressure that you need to overcome. So that is why the pressure drop is the highest, because of hydrostatic value. So this here must be, since it is per meter, that means it has to be 1/10 of a bar for a density of, let's say, 1,000, depending on what is condition and what is refrigerant temperature. So this is really liquid. Now, as we are evaporating, increasing the quality, this density dramatically goes down, and then at some point it starts to go up. It starts to go up when there is enough vapor generated so that it can push all of that liquid along the wall, and sometimes even in generating intermittent flow. And that is what creates this increase. And then eventually, this here has to come to the same value as in horizontal tube. So I'm using this opportunity not to tell you only about 14A and only about micro-fin tubes, but kind of to tell you something about heat transfer and pressure drop, hoping that that kind of refreshing might be also refreshing for you. Obviously, I don't see that too much in your faces, but I'll forgive it. We don't need to share that much enthusiasm, but especially I am attached to this. But anyway, so this is now how it looks in axially grooved. That was for the smooth tube, and here is for axially grooved tube. The shape is the same, but the values are higher. And I will show you later a comparison between these two, smooth and axially grooved. Now, this is comparison of smooth versus microfin tube, that axially grooved, in heat transfer and horizontal pressure drop. For the same conditions, this here blue is mass flux of 100 kilograms per meter square in second, and then 180. The same thing with microfins. So if we compare red to red, this is the same condition, different geometry. Heat transfer coefficient is that much higher, pressure drop is that much higher. And I'll summarize that in 2 slides, and then you see whether it's worthwhile or not worthwhile to use it in your calculations and to purchase and make heat exchangers yourself. Now this is just a different condition, the same thing. So this is the effect of mass flux between blue and, here is heat flux, apologize, between microfin and microfin at a different heat flux, and red to red or blue to blue is the same geometry. And the pressure drop, you see here, we don't see too much of effect. Of course, heat flux doesn't affect pressure drop. Mass flux or mass velocity affects pressure drop. Why would heat flux affect pressure drop? Give you a test. Who knows? Because of acceleration component. Higher heat flux will generate more, and vapor will go faster. And that part, obviously, acceleration component in a pressure drop in these relatively small velocities or small mass fluxes are relatively insignificant. Now, this is a summary. You have an enhancement factor, which is heat transfer in microfin tube versus smooth tube. And pressure drop penalty factor, and you see that it is less or more the same. Average value is something about 1.34, 1.23. These are, so now you could maybe ask, how do I compare these two? We typically use a so-called melty diameter. You assume that the top of the fins are kind of pushed into the valley of the lower part, and you create the tube of a same diameter but smooth. Here it is actual smooth tube because they are very, very similar. Okay, with all of this, you see this is maybe the key of the message about the effect of microfin tubes. If you buy that tube, you will have 34% higher heat transfer coefficient, and pressure drop will be 23% higher. Now, actually, area that is in contact with fluid is almost the same amount higher than this increased heat transfer. Microfins increase the surface area of a tube in contact with refrigerant, and that is the major reason why we have that improvement. So you will see also from videos that microfins here did not change dramatically flow regimes, because if you would have some swirl, that may affect flow regimes much more, and the heat transfer enhancement factor would be even higher than this. Okay, let me now tell you something about visualization. We have first visualization, it's immediately after test section, and this is glass tube that has the same diameter as smooth tube. But then we have made 3D printed, transparent microfin tube to be able to see through the tube and through the outer glass tube, I'll show you that later, what is happening inside the tube while evaporation is happening. With this glass tube, we see immediately after, as everybody else in the world do that. Okay, so these are the flow regimes for these typical mass fluxes of 100, 180, 250 kilograms per meter square and second, as a function of qualities that are shown here, and flow regimes are marked here. SW means stratified wavy, annular, and so on. So here you see what is happening, and you see the difference between smooth and microfin. Smooth and microfin for exactly the same conditions. So I've decided not to put all of these videos here because it will be very difficult for presentation, but you have here pretty clear vision that there is a little bit of difference, but not dramatic difference in flow regime. How that looks like in a flow regime map is presented here. This is very common flow regime map that shows flow regimes as a function of mass velocity and vapor quality. I is the intermittent flow regime. When we are at very low mass fluxes, we have almost sewer flow or stratified flow. When velocity over that stratified flow increases, this is like in the sea, in the ocean, when wind is blowing over stratified liquid, then we have waves. So this is stratified wavy, and at the beginning, when Kelvin-Helmholtz instabilities take place and plug entire tube, then you have slug, plug, or intermittent flow, when plugs and slugs change and move liquid in kind of bubbles and chunks of liquid, and so on. Annular flow at slightly higher mass fluxes and slightly higher velocities, and we didn't push too much to misty flow. Okay, here you see now videos. I hope you see it well. On the left side is a smooth tube, on the right side is a video with a microfilm tube, and you see the difference at the given condition. So what we see is a slightly higher level and even more liquid in a smooth tube than in microfilm. Microfilm is kind of spread also a little bit. What is sent on the top, it stays a little bit on the top due to surface tension between these microfilms. When we go to slightly higher quality of 20% from 10%, we see stratified wavy in both cases, and you see this here how these waves from time to time become very high, and that is a well-known Kelvin-Helmholtz instability. This is when waves splash on the top and sometimes close the tube, create a plug, and then you have slug, plug, intermittent flow. This is at a little bit higher qualities. So now this quality is 0.5, and we see, like on the sea, those of you who have been sailing well, when the wind is very high, then you start taking liquid off the surface of the waves, and it splashes at the end, and it ends up here on the walls and create a situation to switch to annular flow. Because this here is small, you see that here on the top there is a small film. That film will thicken and become annulus. And that is more and more pronounced here, and we would call this annular flow. Now, this liquid vapor interface is, we have developed various numerical or statistical methods, and then basically to get the data from the video to have a line, and you see that the line that is showing the liquid level in smooth tube and in microfilm tube. And that when you show just these lines, so basically to transpond the video into lines, into levels, here is what you get. This is with a smooth tube, blue, and red is microfilm tubes. Much more erratic, yet lower level that we see. Liquid is more held between the microfilms on the top of the tube. This is a diabetic visualization test section. What do you see here? Inside, this a little bit more kind of yellowish grayish. This is a transparent plastic 3D printed tube with the microfilms inside. These microfilms are a copy of microfilms in aluminum tube, while outside there is a annulus for water to flow. This water goes here and leaves the section, visualization section here. If you look a little bit closer on these ends, you see holes. These holes are made there to unify the velocity in the annulus. So otherwise, the top would get a little bit more flow than the bottom. That is quite sure. How it looks like, this is the video. Let me go back. Okay. This is the video. Maybe this is now. Okay. This is that video. What do you see? You see a generation of bubbles at the lower left end. And you see that it's some initiation points where roughness is a little bit higher or temperature a little bit higher, we have a little bit more of these bubbles being generated. This is high-speed camera. That point here, it looks like that these points that you see are always stationary. In reality, they move. It is just when you take several seconds of a video. When we take now the details, this is how that generation of bubbles look like, very, very slow down, but you see how much is here velocity. This here is an interface between vapor and liquid. So you see a liquid level rising from the bottom to the top, and then this wave passing through all of these bubbles that have been generated at the wall, along with those bubbles that have been entrained in the flow, pass by very rapidly. Look at this. So these bubbles are everywhere. So expect to see much more of these videos in one of next KGH meetings. And the summary, I already told you that I should be probably stopping. I'm running, of course, too long. So summary is, it is with that axial grooved aluminum tube, we improve heat transfer, increase the heat transfer, we pay some price in pressure drop. It looks like that we gain more in heat transfer than we are losing in pressure drop. Even when you look into number, in principle, we can tolerate a little bit higher pressure drop when we gain improvements in heat transfer, because that is the major objective of the enhancement. I will stop here.